We'll now have an example of finding the transfer function, the impulse response, and the frequency response. This is slide 19 of part 4B. Typically, we are given a differential equation, and in this case, we are given some initial conditions. At time y, at time 0, the y value is 3, and we are asked to find the transfer function. Now, remember that when we are asked to find transfer function and we are given initial condition, we must ignore it. So, remember, to get the transfer function, we perform the Laplace transform on the differential equation with 0 condition. The initial condition is a red herring, meaning that it is useless. It's trying to fool you. If you put it there, you will not get the transfer function. You get something else. Okay? Now, what is the transfer function again? It describes the relationship of the output, which is ys, over the input. So h of s is equals to y over s divided by s of x, x of s. And notice that this operation is done as multiplication. So in the time domain, everything was done in the derivative. Y and x are related by derivative. But in the Laplace domain, x and y is related by, divisions and products. So ys equals hs times x of s. Now, always remember, we are interested in, when we are interested in transfer function, it is the zero state condition, or sometimes it's called a relaxed condition. All right. Now, in fact, when we find the transfer function, we can immediately find something called the impulse response. The impulse response is let's say this is the LTI system. We will fire the impulse. So this is delta of t. And out comes the impulse response, h of t. Note that the LTI system must have 0 condition, 0 initial condition, or 0 is a relaxed state. Now, if delta of t is fired into an LTI system and you get h of t, then let us perform the Laplace transform of delta of t. What is the Laplace transform? It is 1. The value 1. So what happened is that when xs equals to the input, when xs equals to the delta, xs equals to 1. So ys is equals to h of s. Now, what happened now is, we know that in the time domain, when we fire the impulse, we get h of t. Now, when we view this in the s domain, xs equals to 1, ys equals to h of s. So, the inverse Laplace transform of h of s is equals to h of t. So that's the idea. All right. Okay, again I repeat. To find the impulse response, we must have 0 initial condition. This is the same as finding the transfer function. So everything is in agreement here. So we have just discussed h of s and h of t. Now, let's go to the next page, and we will continue to discuss how to find the frequency response. Simply, once we have h of s, all we need to do is to substitute s equals to j omega. Where is s equals to j omega? So if you draw s, what is s? So s is a complex number. A complex number is some sigma. So this is the real part. So this is 0, this is 1, this is 2, this is minus 1, minus 2, minus 3. And this is j, and this is 2j, and 3j, and so on, minus j, minus 2j, minus 3j. So this 2D surface is the complex number, is the complex plane. When we set sigma equals to 0, we are interested in this line, only this line. the line of complex number stretching from minus infinity to infinity. So when we say that we are interested in evaluating h of s for s equals to sigma equals to 0 and the entire j omega, we are evaluating this line along the s plane. Okay, and when we do that, then we get the frequency response. Of course, please remember that for this evaluation to not blow up, not to go to some infinite number, the system must be Bibo stable. Bibo stands for bounded input, bounded output. When the system is stable, then the region of convergence will include the j omega axis, which is this axis. Right. What's useful about hj omega? Now, hj omega, its name says frequency response. Frequency of what? Actually, it's the frequency of the complex exponential. Ej omega, which whatever frequency we are interested in. So this omega is the same as this omega. Now, remember, sum of two complex exponential give you the cosine or the sine. The sum or the difference give you the sine or the cosine. So when we talk about complex exponential, it equally applies to sine and cosine. Now, hj omega will tell us how this cosine or sine will change its magnitude as well as phase shift when it passes through the system, but only in the steady state. So you realize that when we use frequency response, we only calculate steady state, meaning what will happen after a long time. So what happened in the LTI system is when we send a cosine in, a cosine will come out, the same frequency, only its magnitude and its phase is shifted. Okay, when it's in steady state. Why do I keep on talking about steady state? Because something happened when we initially send the cosine. There will be a transient state, and we'll see that in the next example. All right. Maybe some examples now. We'll have a concrete example here. We have a very simple first order constant coefficient linear differential equation. Simply dy dt is equals to, or dy dt plus yt equals to x of t, and we are given some initial condition. Again, when we're asked to find h of s, this is ignored. Okay, we should ignore it unless we're asked to find yt, then we cannot ignore it. If we're asked to find h of s, we must ignore it. So how to find h of s? Remember, the first step is to take the Laplace transform and use the differentiation property. So dy dt become s of ys. Actually, it's minus y naught, but we ignore it. Yt become ys, xt become xs. So we are left with this equation. To find h of s, we want to form this equation. So what do? We collapse all the ys together. So ys equals to s plus 1. And that's it on the left hand side. Now to collect ys over x of s, we will get h of s, and we found the very simple transfer function. Now to find the impulse response, we take inverse Laplace transform. Inverse Laplace transform by lookup table. Okay, so in the exams you have to copy that lookup table into your cheat sheet. It will not be given, and then you just look it up. 1 over s plus 1 becomes e minus 1t. That's it. So we have found h of s, and we have found h of t. Alright. Okay, now let's deal with this. We have found h of t, and let's fire an impulse at time 0. So x of t equals to this delta function. So y of t, remember, is described by the convolution equation. So it is e minus 1t convolved with the impulse, and therefore we get back the same output. Y of t is equals to this. Now, if we are interested to find something called the frequency response, we take the S domain, H of S, and then we substitute S to be j omega. That's all. So now here and now here. And what happened? Then now we have a function called the frequency response, and this frequency response does nothing but if you substitute different values of omega. So for example, you substitute 1, so we are evaluating h of s equals to omega equals to 1. So I should write it this way, omega equals to 1. Then the answer is, also I should say j omega equals to 1 is equals to 1 over j1 plus 1. Okay? And then this is the complex number. So you must need to know how to divide complex number. So to get, then you will get, so this complex number have to be changed into magnitude as well as the phase. Alright. And once you have changed that, you have the magnitude and you have the phase, and you can put it back into your complex exponential. So your complex exponential was ej omega naught. So the magnitude is hj omega naught, absolute value, multiplied by the original complex exponential ej omega naught t, and now we phase shift it by this guy. Okay. So this little slide shows you how to go from h of s to h of t to h of j omega from a differential equation. So I repeat, you must ignore the initial condition when you are deriving h of s. Now, please be careful. I have calculated y of t using h of j omega. And when we do that, this output is called the steady state response. In the next slide, I will show you that the steady state response is only part of the answer. There's something called the transient response.